As it turns out, the hydrogen atom is the only atomic or molecular system that we can solve exactly using quantum mechanics. When we turn our attention to multi-electron atoms, so the simplest multi-electron atom would be a helium atom with a proton and 2 electrons. When we turn our attention to these multi-electron atoms, we all of a sudden have a problem that involves more than 2 bodies. And this 3-body problem becomes very difficult to solve, and we can't solve it exactly. But what we can do is approximate the solutions. So that's what we're going to talk about in the next few videos. In this video, we'll set up the Hamiltonian for this problem, and then we'll see how we can apply some approximation methods to solve that Hamiltonian problem. So in the helium atom, where we have a nucleus that is charged 2+, and we have 2 electrons, we have several forces that we have to take account of. So our potential energy is going to be involved with the attractive potential energy between electron 1 and the nucleus, the attractive potential energy between electron 2 and the nucleus, and then we also have a repulsive Coulomb potential between the 2 electrons. So if we designate R1 as the distance that electron 1 is from the nucleus and R2 as the distance that electron 2 is from the nucleus, then the distance between the 2 electrons at any given time is the difference between R2 and R1, that vector difference. So that means that our potential energy term, our potential energy operator, is going to be the charge on the nucleus times the charge, the fundamental charge squared, divided by 4 pi epsilon naught R1 for the Coulomb potential, attractive potential between electron 1 and the nucleus. And then we have to add in the potential energy between the nucleus and electron 2, so that depends on R2. And then we also have the potential difference between our 2 electrons, which depends on the distance R1 minus R2. In addition, our kinetic energy operator is going to depend both on the motion of electron 1 and the motion of electron 2 around the nucleus. So if we do this in center of mass coordinates, remember that the reduced mass between the electron and the nucleus is going to be essentially the mass of the electron, and so we can think of the nucleus as stationary and the electrons as moving about the nucleus. So we have those 2 kinetic energy terms, and so we have to account for the momentum of electron 1, and we have to account for the momentum of electron 2 in our kinetic energy terms. So the full Hamiltonian contains a term for the kinetic energy of electron 1 and the potential between electron 1 and the nucleus. That's just exactly like the hydrogen atom, the Hamiltonian, for electron 1, except that the nucleus has a charge of +2 instead of +1. So we're going to combine those 2 terms and call that H hat 1. That's the regular potential and kinetic energy for electron 1 relative to the nucleus. Plus, we have a term for the kinetic energy of electron 2 and the potential energy of electron 2, the attractive potential with the nucleus, which is exactly like our hydrogen atom potential. So we're going to call that H hat 2. And then we have this extra term in the potential that has to do with the repulsive potential between the 2 electrons. So plus E squared over 4 pi epsilon naught R2 minus R1. So notice that the potential energy, the attractive potential energies are negative, and the repulsive potential energy is positive. This overall Hamiltonian is very much like the hydrogen atom Hamiltonian, except that it has the addition of this repulsive term. because this repulsive term depends on both the coordinates of electron 1 and electron 2, we cannot separate this Hamiltonian and write it in terms of a solution for electron 1 at times a solution for electron 2, because the coordinates of electron 1 and electron 2 are combined together in this repulsive term. So because it's not separable, that's what makes this difficult to solve and makes it so that we have to solve this using approximate methods.